A wire in a plane has the shape shown in the figure. Two arcs of a circle connected by radial lengths of wire. We are to determine the magnitude of the magnetic field at the point C in terms of the two radii r1, r2, the angle subtended by this figure called theta, and the current I. For this calculation, we're going to be using the Biot-Savart law, and this law tells us how to make a magnetic field out of infinitely many infinitesimally small lengths of current. Each length of current will have a length dl. The vector dl is directed in the same sense as the current. This vector dl is crossed with r hat, and the whole thing is divided by r squared. You can think of this problem as being the magnetic field equivalent to the old problems of integrating over a charge distribution, except this time we integrate over a current distribution. Whenever we solve the Biot-Savart law, we're going to need to make replacements underneath the integral for three individual terms. The first term will be dl. The second will be the distance r, which we recognize is not necessarily a radius, but is in fact the distance between the piece of current and the point P, or point C in this case, where we're doing the calculation. And finally, we need to attend to the direction vector. The direction vector will be handled here by a shorthand notation that I'm calling cross r hat. Mathematically, what we know about the operation of a cross product is that the cross product results in a vector whose direction is perpendicular to the two vectors that have been crossed against one another. This is the mechanism by which a line of current has in fact made a circle of magnetic field that surrounds it. Imagine, as an example, a line of current that is pointed towards you as given by this purple circle. If we were to attempt for that circle to perform a calculation, over here at the green dot, we recognize that the dl will point out of the screen and that the r hat will point in the direction towards the point P. Using the right-hand rule, we recognize that the dl crossed with r hat will be in a direction perpendicular to the plane formed by the two, and in this case will be over here. If we had placed the point P up here, we would get this direction, and so on, demonstrating that the dl crossed with r hat yields magnetic field contributions that make circles around the lines of current. If you remember problems in which we integrated charge distributions, we used our intellect to deduce the direction of the final answer, and then sum only those components that had contributions in the direction of that final answer. This is the way that we handled away hat for charge distributions, and that is in fact how we will handle cross r hat, by adding up only those contributions which are in the direction of the final result. Let's begin. Our current distribution has multiple pieces. One piece is the inner arc, two pieces are the radial portions, and then the final piece is the outer arc. In principle, these would make four contributions. However, one simplifying feature of this problem is that the current along the two green radial pieces is directed straight towards the point C. In this case, the dl for those and the r hat is in the same direction. Therefore, the cross product will yield 0, and we will have only two contributions. The first contribution from the inner arc, and the second contribution from the outer arc. To understand the directions of these contributions, we can use the right-hand rule. Curling the fingers of our right hand and laying them in the sense of the blue arc, we'll see that our thumb will point upward at the point C. Similarly, if we were to do the same exercise for the purple arc, our thumb would point inward towards the screen. For this reason, we will consider the cross r hat term to be producing a positive result for the blue curve, meaning out of the page, and a negative result for the purple curve. Let's begin starting with the contribution from the blue arc. We recognize that this line of current should be treated in cylindrical coordinates, and this particular line subtends the angle theta. Therefore, our dl will be in the theta direction and be related to a d theta, but d theta is not a length element. In order to get a length, we need r times d theta, and for all pieces of current on the inner arc, they all have the same radius, and that radius is r1. The second item to be dealt with for the inner curve is the radius parameter r. This is the distance between any piece of current and the place where we're doing the calculation. And because the place where we're doing this calculation is the point C, that radius is simply r1 itself. Finally, as discussed a moment ago, the right-hand rule has told us that all of the contributions from the purple arc will be in the direction perpendicular to the screen and outward towards you, and we've decided that that is called plus. And so our handling of the cross r hat, which is the directionality term, is to simply insert a +1 into our integral, and then we're ready to begin. Bringing the current outside the integral and substituting our various pieces, we get an integral of this form. In order to complete the problem, though, we're going to have to place some limits on the angle theta. We can choose any location as the 0 for the angle theta, and for convenience, we're going to choose, in this problem, the 0 to be on the left, so that the theta itself will be integrated from 0 to the final full theta that the arc subtends. Notice that since the radius vector is a constant, it comes out of the integral, and that the integral of d theta from 0 to theta is simply theta. And so this is the contribution of the inner blue arc. The outer purple arc can be calculated in a very similar manner. The length element dl will be r2 times d theta. The radius, distance between each piece of current and the place where we're doing the calculation, is r2. And we will handle the cross r hat term by using a -1 because we recognize that the contributions from the purple arc are directed into the page. When we plug in these series of parameters into the same integral, we notice that there are only two changes. r1 is changed to r2, and the cross r hat produces a minus sign, so that the magnetic field contribution is negative μ0I over 4 pi r2 times theta. Finally, if we wish to get the total magnetic field at the point C, we simply have to add together these two contributions, and when we factor out the common terms to the front of the expression, we will find μ0I theta over 4 pi times the quantity 1 over r1 minus 1 over r2. And this completes our calculation of the magnetic field at the point C.